Hello, today we'll be looking at problem number 60 in the book, chapter topic 4. It's the famous pulley problem on a slanted um, surface. So, in a nutshell, this problem is stating that you would have a 5 kilogram weight on about 40 degrees, and then it will be connected to a frictionless pulley, which will also be pointing down with the rest of the rope, which is non-stretchable, and we're assuming there's no friction here, which is going to be at 10 kilograms. And this is what basically the problem is stating. Next, they are going to ask you to find the acceleration of the system, and you're going to have to calculate the tension of the string itself. Now, let's take a look at what are the forces that will be in effect here. First thing first, realize that this box is going to have some sort of M2G. We're going to call this mass 2 and this is mass 1, just so we could, I guess, make a distinction between them. This, on the other hand, is going to have a different type of direction of the force here. It's going to be M1G. However, the force that we're going to uh, really look into here would be the one on X. And we're talking about x-axis here, we're talking in relationship to parallel of the slant, right? So what we're going to do is to find the x, you would do the sine of that angle times the mass times the gravity, right? And the way you could really look at this is if you imagine the box over here, it's going to be pointing down, and it's going to be pointing down right here. This would be your y component, x component. This is what you're really pointing at. And if you're at 40 degrees here, this means this right here would be 40 degrees. Think about it. If you would go down this slant right here, you would decrease this angle. This will also decrease proportionally or indirectly. In fact, this becomes 39, this becomes 39, and so on until you're at 90 degrees here and you're at pretty much um, 0 there. Um, with that in mind, I could go ahead and state that this would be a right angle. This would be my x component that I'm interested in. These are two equal vectors, basically. So long story short, you would use opposite over hypotenuse, which leads to usage of sine. We know the angle to be 40, and the hypotenuse would be your mg. So I would make sure your calculator is in degree mode. We're going to say sine of 40 timing the mass, which is in this case 5 for M1, right? Because this is what's going to be affected by gravity here. And this is going to yield an answer of 31.49. Now, let's pause here and talk about signs here. And when I say signs, I mean negative and positive. What's negative and what's positive? Well, that's for you to decide. But I would say that as this motion happens, I'm going to assume that we're going positively in a positive direction because that's where my motion is going. And anything that would hinder it or slow it down or go in the other direction in a way would be negative. So in this case, I could, assume that um, this is the magnitude, and then I'm going to apply my vector sign, which is negative. This force, I'm going to call it the force of M1 here. Let's call it that M1 with gravity x vector. Negative 31.49. And the units on that would be newtons. So we're going back here and we got something figured out, right? The second force here would be pretty straightforward. There are no angles, it's just a straight down movement. So it would simply be mass 2 times gravity, which is equal to 10 times 9.8 which is equal to 98 newtons. Now, we said anything that's moving in that direction is going to be positive, right? Now, we need to find the acceleration of the system. And when we say the acceleration of one box, the other box has to have the same acceleration. So I have to take the basically the mass of both boxes in account when finding this acceleration. So I do have a positive 98, and I have a negative 31.49, right? And that would be my net force of the movement. And since this is my net force of the movement, I need to find my net acceleration for the system, and that would require me to go ahead and take both masses into an account. This is going to be a positive 66.51, and to put that in acceleration terms, I would have to do the total of force here, which is 65.1 newtons, equal to mass times acceleration. This is going to be total. So this would also be total anyway. That's what we're interested in. We know that acceleration for box A has to equal box 2. For box 1 and 2 have to have same acceleration. Hence, they're both on the same system and they're tied by the same 10th rope. So, when I add both masses, I get 15, right? 5 plus 10. And I go ahead and I'll divide both sides by 15 to find my acceleration. My acceleration should equal 4.43. And for acceleration, as you might remember, the units will be meters per second squared. Now, that we have acceleration in place, I have the net movement. This is what we're going to see. When these boxes fall, these two boxes are going to kind of fall to the left. When they do so, what you're going to observe is an acceleration of 4.43. And with that in mind, now we know the net movement, and now we know the net force. If we want to find tension, here's where it gets a little bit trickier, right? You kind of want to draw like the body diagram of each of these boxes. And let's say we draw the box number 2, which has 10 kilograms on it, right? We know two things. We know that tension is what's keeping it from free falling, right? There's some sort of tension of the rope that's holding it in place. You might tend to think that this tension would be equal to my box 1 pull, but that might not be fully the case here. So let's see what we have. What we have is a free fall M2G, which is equal to, as we defined it, 98. And then we have what we can observe. What we observe at this acceleration is M could be transferred into terms of M2A, which is going to be the force that this box actually going to feel as it falls. It's not going to feel the full 98 because, well, it has some sort of negative force of tension acting against it, but we know what we're really going to observe. We'll be observing the M2A. So in that case, I can say that my M2G is going to be limited by my tension to only allow me to observe M2A. And here the signs will also make sense. This is positive, this is positive, this is negative, since we assume that everything that's moving in this direction is positive. And then I go ahead and I plug in my 98 minus t, and then M2A would simply be 10 times my acceleration that I found here, which is 4.43 meters per second squared. And now I could go ahead and actually evaluate this equation. 10 times 4.43, and then that's 44.3. Then we're going to move the 98 to the other side, which is going to be a negative 98, so it will be 44.3 minus 98. And on the other side, we still have that negative t, which we'll take care of in a second. We'll do 44.3 minus 98. That yields an answer of negative 53.7. tension here is negative. And from this point on, you would all you'd have to do is take get rid of the negative signs, yielding that 53.7. Now the tension should be negative here, and this means that we made some sort of mistakes with the signs as we were going through this problem. To figure out where we went wrong, we would have to trace our steps and see what happened. So T, we gave it a negative sign, which is good. We said M2G is going to be with the negative, and this negative sign is why we got a positive number. We presumed that T has to be negative, so we gave it a negative sign ahead of time. Realistically, what I should have done is I should have approached it as a sign neutral um, value without any presumptions of what has to be, and then I would have gotten a negative value out of it. However, in this case, I know that T has to be negative, so I will keep the negative sign um, without any presumptions of what it has to be. Because if I presume it's something, I better keep that thing, right? So realistically, what you could have done too is you said, I don't know what the sign's going to be. I'm just going to solve. I know that I'm limited by it, but I don't know by how much. You'd have gotten your T to be positive, and you would have done the math. And it would have yielded you a 9.8. I just want to show you what would happen if you assume that you have a negative sign right off the bat, which is not a bad assumption to make in this case. However, when evaluating such values, you might be at your best interest to hold off the sign assignment until you know what your value is, and then it would be straightforward. This value is also in newtons, um, and that would be your tension that you're going to feel. Now, you might ask me, well, what happens if I do calculate my tension on the other end of the spectrum, right? Well, what happens if I look at box A? Why didn't I use that? Well, box A would be a bit more, I don't want to say a bit more complicated. It's just that tension and the force of movement are equal, and the only thing that's pulling back is gravity. So we could still do it. So the way it will happen is I'll still say the same thing. T is going to be pointing to the up to the left, and then back will be that 31.49 we calculated. So this is going to be negative 31.49. And then what's going to happen essentially is I'm going to use my acceleration. I know that my tension is going to be the difference between my values here. So this is going to be M1A, right? If I use that box, it's M1A. This is tension from I don't want to call it the one side, but essentially T2 and T1 got to be equal since this is a non-friction pulley and it's a non-stretchable rope. So this T, let me draw it better, is going to be equal to, well, let's think about it, right? You got an acceleration that's ma, that's being felt, that's the net that's being felt, right? So that's what I'm seeing, that's what we know things are going to be equal to. And then I have tension. Tension is going to be pulling the same direction as the acceleration, right? That is going to be hindered by that 31.49. Now I already know the value and the sign of this vector, so I'm good to put the sign here. Now watch what's going to happen. I could evaluate this right now. I know mass 1 to be 5, and I know the net acceleration to be the 4.43. So M1 is 5 times 4.43. I go ahead, that's 22.15. That's good stuff. That's going to be in Newton as well. It's going to be equal to my, I don't know why I have two equal signs here. Negative 31.49. Tensions here going to be positive. And now I would add 31.49 to both sides, which means it's 22.15. plus 31.49. That would be 0.105, and that would be 53.64, which is very close to the 53.7 we got back there. It's probably some rounding off by 0.06, which is great. And as you can see, tension is pretty much equal between the two ends, no matter where you calculate it. The reason one of them is negative and one of them is positive because the tension of one rope is pulling up on box A, and the tension of the second rope, actually the tension on the second mass is pulling up against the mass, right? And it's slowing that movement. And on box two, uh, this box right here, actually box one, is going to be moved by that tension. And that's how it propels its movement throughout the system. And that's why the tension here is positive. That's why students seem to struggle with, and myself sometimes do struggle between the difference in signs in tension, and it's actually, it really depends on where you're looking at tension from. Tension has two ends to its force. It feels the 53.6 or zero point 0.7 throughout the rope, but if you look at it from the end of one object, it might be helping it move in the direction that you decided to be positive, or from the other end, it might be hindering it from moving to the place it wanted to, like we saw over in box two with the 10 kilograms. All right, I hope that this little bit of uh, walkthrough helped. And well, don't hesitate to email me if you had any other questions.